In the series Advanced Mathematics, we are going to start now lecture 8 of chapter Vector Calculus, and in this lecture we will talk about Stoke's theorem. So Stoke's theorem states that suppose we have a open surface, any open surface is there, and it is being bounded by, we are talking about, suppose this is the surface we are saying, and it is bounded by a closed curve. This surface, it is bounded by a closed curve C. This is the surface S, and f vector xyz be a vector point function which is continuous and has continuous first order partial derivatives in a domain that contains S. Then Stokes' theorem states that the line integral f vector dot dr vector, this is equal to the double integral of curl of f vector dot n cap into ds. So we are calculating the line integral of f vector dot ds about this curve C, then it is equivalent to the surface integral of curl of f vector. So we prove this theorem for a particular case when we are saying that the surface that we have, this surface we are talking about, it can be expressed in the form, it is z is equal to f of xy, then y is equal to g of zx, h is equal to x is equal to h of yz, where f, g, h are continuous functions and have continuous first order partial derivatives. So we are saying if this f function, we are having f vector, we can write it as f1 I cap plus f2 j cap plus f3 k cap. Then we have f vector dot dr vector, we are saying f vector dot dr vector, this is equal to f1 dx plus f2 dy plus f3 dz. Now curl of f vector, that is equal to I j k, we are talking about curly by curly x, curly by curly y, curly by curly z, it is f1 f2 f3, and when we open this determinant we obtain the answer in this form. So we are saying if we use this result, the Stokes theorem, it reduces to the form that the line integral of f1 dx plus f2 dy plus f3 dz, that is equal to, we are saying in place of dx we can write it as n cap dot I cap into ds, then in place of dy we can write it as n cap dot j cap into ds, and the third we have it is n cap dot k cap into ds. Now suppose we are saying the equation of the surface be phi xyz, that is equal to z minus f of xy, that is equal to 0. So suppose we are saying these are the axes that we have, and this is x-axis, y-axis and z-axis, and this is the region we are talking about, and this is the bounding curve that we have, this is the bounding curve. So the projection of this curve on the xy plane, if we plot, this is the curve C, this is the projection of this curve in the xy plane, and R is the projection of S. This surface, it has, this is the projection of this surface S. This is the surface S, this R is the projection of this surface. Then we are saying by the Green's theorem, if we apply the Green's theorem over here, we get it is integration of f1 xyz dx, that is equal to, this is over the curve C, we are writing this is equal to integration, the closed integral, the curve we have, it is closed, over C star, we are talking about this is over this projection, and the function we have now, it is f1 of xy, and in place of z, the function we are writing, it is z is equal to f of xy, so we can write it as f of xy into dx, and by Green's theorem this is equal to double integration over R. minus curly by curly y f1 of xy f of xy into dx dy, and we are writing this is equal to, if you apply this partial derivative over here, this is equal to minus double integral over r. The values we have, it is curly f1 by curly y plus curly f1 by curly z into curly f by curly y. We are having these two functions. This is the capital F1 we are saying, and this is f of xy, which is coming from this equation of the surface, and we are saying this is into dx dy. So this is the value of this integral. This is the value of this integral. Now equation of the surface S is phi is equal to z is equal to this. So we have to calculate the normal vector over here. If we calculate the normal vector, it is given by gradient of phi divided by mod of gradient of phi. And if we differentiate this value, we have this z is equal to, this is the surface. The answer we get, it is minus curly f by curly x I cap minus curly f by curly y j cap, then plus k cap and mod of this whole value. And if we substitute these values, we obtain n cap dot j cap over n cap dot k cap, that is equal to minus curly f by curly y. So if we substitute this value, in the given equation, we obtain that integration over c f1 dx, that is equal to double integral over s. Now in place of curly f by curly y, we are substituting it is minus of this, and in place of dx dy, we have the value, we know that dx dy, that is equal to n cap dot k cap into ds. So if we substitute these values over here, we obtain it is minus curly f1 by curly y plus curly f1 by curly z n cap dot j cap over n cap dot k cap, and we are multiplying it with n cap dot k cap into ds, and we are writing this is equal to double integral over s curly f1 by curly z n cap dot j cap, this is n cap dot j cap, minus curly f1 by curly y into n cap dot k cap into ds. Now similarly, we can calculate the value of this line integral of f2 dy, and we can calculate the value of this line integral f3 dz. And if we add all these values, we are talking about this integral f1 dx, this integral f2 dy, and integral f3 dz. We obtain, this is the left hand side, and on adding all these values, we obtain the result in this form, and this is basically the curl of f vector dot ds vector, and this is what the Stokes theorem is. This value we are saying, this is basically the double integral curl of f vector dot ds vector over the surface S, and this value we have, it is the integral of f dot dr vector. This is the circulation of this term. So this is what Stokes theorem states. Next we have is Green's theorem in plane as a special case of Stokes theorem. So we are saying that the function f vector that we have, that is equal to phi I cap plus psi j cap, then f vector dot dr vector, that is equal to phi dx plus psi dy, n cap we have, that is equal to k cap. We are talking about the plane, this is the in the xy plane, so the normal will be in the direction of z axis. Now curl of f vector, if we calculate, the value we will obtain, the curl of this vector when you calculate, it is curly psi by curly x minus curly phi by curly y into k cap. The value of ds we have, it is equal to dx into dy. So if we apply the Stokes theorem over here, we are saying it is integration f vector dot dr vector, that is equal to double integral over s curl of f vector dot n cap into ds. Now if we apply this function f over here, we get it is integration over c phi dx plus psi dy, that is equal to double integral curl of f vector dot n cap, the value we have, it is curly psi by curly x minus curly phi by curly y, k dot k is 1 into dx dy. This is the value of ds that we have, and we are saying this is the Green's theorem in the plane. Now next we have to prove is that integration closed integral f dr vector, that is equal to double integral over s ds vector cross del of f. Now let a vector be any constant vector, then by Stokes theorem we have integration f a vector dot dr vector, that is equal to double integral over s, it is curl of f a vector dot ds vector. Why we are using this result? We have to find the relation between dr and ds, and we know that Stokes theorem gives us the result. But the problem over here is that this function f, it is a scalar function. So to convert this into a vector function, we have used this f into a vector and we have applied the theorem. So this is equal to, we are writing it is double integral over s curl of f of a vector means del f cross a vector dot ds vector. Now this implies us that integration over c f dr vector dot a vector, this is equal to double integral over s, then we have del of f a vector ds vector. This is, we have the scalar triple product. We can write this is equal to double integral over s, we can interchange the positions, we are writing it is ds vector, then del f, then a vector, and we can write this is equal to double integration over s, it is ds vector cross del f dot a vector. Now compare both these values, what we obtain is, since this a vector is an arbitrary constant, we obtain that integration over c f dr vector, that is equal to double integration over s ds vector cross del of f. This is the result that we obtain, that we have to prove. Next we have to evaluate this integral on the surface of intersection of the cylinder x square plus y square is equal to a square and x square plus z square is equal to a square in the first octant, and it is given that the value of a we have, it is this. So if you look at this value, this is, we are given it is double integration of del cross a vector dot n cap into ds, it is over this surface. We are saying by Stokes theorem we can write this is equal to integral over c, in place of this we will have a vector dot dr vector. Now we are talking about two cylinders, we plot this region, we are talking about two cylinders. One is the cylinder, it is x square plus y square is equal to a square. This is x axis, y axis, z axis. So we are saying it is some cylinder in this form, that it is like this. This is the cylinder in this form. We are having x square, this cylinder we are saying this is x square plus y square is equal to a square. Then we have x square plus z square is equal to a square. So x square plus z square is equal to a square will be a cylinder over here, and it will look something like this. This is the cylinder we are talking about. This is the cylinder. I am extending this cylinder on this side. So we are having some regions over here corresponding to this cylinder. The portion we have over here, it is like this. This is the portion of this cylinder, and the second cylinder, corresponding to the second cylinder, we have some curved portions like this. So we are talking about this region over here. Now it is being given that we are talking about the first octant. So we are saying in the first octant, it is being bounded by the three planes. This region, it will be bounded by the three planes. On this side, it will be bounded by this side and this side. From the three sides, it is being bounded by the zy plane, xz plane and xy plane. So if we talk about the bounding curves, what we obtain is, we have the first curve, we have it is C1 we are writing. It is the arc in this figure. If we talk about, it is the arc corresponding to this circle AB. We are saying it is C1 over here. Then we have the line segment. We are talking about this line segment BP. This is corresponding to this region over here, and it is varying from, we are saying this line BP, it is corresponding to this line over here, and this we are saying it is C2. Then we have the line C3, that is PC. Now if we look at this figure over here, we are saying this is the line PC that we have. So this line PC, it is corresponding to this line over here, this line that we have. This is the line PC. This we are saying this is C3. This portion, it is C2. This is C1, and last we have it is C4, that is the arc CA. We are having the arc, it is starting from the point C and going up to A. This is the arc C4 we are saying. This is corresponding to this portion of the cylinder, and these are the regions shown over here. We are saying C1 is the arc corresponding to x square plus y square is equal to a square, z is equal to 0 in the first octet, and the equation of this circle, it is written over here. It is x is equal to a cos theta, y is equal to a sin theta. C2 is the line segment from B to P. Then C3 is the line segment from P to C. Then we have C4 is the circle x square plus z square is equal to a square and y is equal to 0, and its equation, it can be written in this form. Now we have to calculate the value of this integral. We are talking about this integral. We have to calculate the value of this integral on all these surfaces C1, C2, C3 and C4, and we have to add all these values. Now if we calculate this integral on C1, we are saying the equation we have over here, it is x is equal to a cos theta, y is equal to a sin theta, z is equal to 0. The value of dx we obtain, it is minus a sin theta d theta. Dy we have, it is a cos theta d theta. So when we evaluate this integral, it is integration over C1 a vector dot dr vector. If we substitute these values, the integral will become, it is integration minus of a cos theta plus 3a sin theta minus 2 into a cos theta d theta, and in this case the theta is varying from 0 to pi by 2. We are saying theta is varying from 0 to pi by 2. The angle that we have, we are talking about the first octant and portion of the circle. So we are saying it is varying from 0 to pi by 2, and if you solve this integral, you will obtain these calculations. These are shown over here. When you solve this integral, the answer you will obtain, it is equal to minus pi a square by 4 minus 3 by 2 a square plus 2 times a. Next we are calculating the value of the integral on the curve C2. On C2 curve, we are saying x is equal to 0, y is equal to a. So we obtain dx is equal to dy is equal to 0, and z, it varies from 0 to a. So we have integration over C2 a vector dot dr vector, that is equal to integration 0 to a z dz, and the answer we obtain, it is 1 by 2a square. Similarly on the curve C3, we have x is equal to 0, z is equal to a, so this implies us dx is equal to 0, dz is equal to 0, and y varies from a to 0. So we are having the limits over here a to 0, and when we substitute these values in the formula, we obtain it is minus 3y minus 2 dy. We have substituted in a dot dr. So the answer we obtain it is minus 3 by 2 y square plus 2y, limit we have a to 0. So answer you obtain it is 3 by 2 a square minus 2 times a. It is 3 by 2 a square minus 2 times a. Curve C4. The equations we have over there, x is equal to a cos theta, z is equal to a sin theta, and the value of y we have it is 0. So we can write dx is equal to minus a sin theta d theta, and dz is equal to a cos theta d theta, and this theta it is varying between theta is varying from pi by 2 is less than equal to theta is less than equal to 2 pi. This limit is because we are saying the circle that we have over here, this is our xz plane. If we talk about the quadrants over here, we are saying this is the xz plane. We have this is the first quadrant, then second quadrant, then we have somewhere over here third quadrant and fourth quadrant. The circle we are talking over here, it is starting from this point, it is going up to this, so it is moving between second, third and fourth quadrant. So we are having the limits of theta, they are varying from pi by 2 to 2 pi. So if we substitute these values in the value of a dot dr, the answer we obtain it is integration over C4. It is a dot dr means we are saying it is a square cos square theta plus a sin theta into a cos theta d theta, and the limits we have over here, it is varying from pi by 2 to 2 pi. These are the limits that we have. Now if we open this integral, the answer we obtain, these calculations, these are shown over here. This is a vector dot dr vector. We are obtaining this integral, and on solving this value, the answer we obtain it is equal to minus 2 by 3 a cube minus a square by 2. So we are saying the total value we have, it is sum of all these values, the sum of all these 4 integrals, the values we have obtained. So on adding these values, the final answer that we obtain, that is equal to minus of a square by 12 3 pi plus 8 a. So this is the final answer that we obtain in this case. Next we have is using the Stoke's theorem, we have to evaluate this integral where C is the boundary of the triangle with the vertices, these 3 vertices. So if we plot this triangle, we are talking about, this is the figure we have. Now look at this curve, we are talking about this is the curve C that we have, and this is the region bounded by this curve, this is the open region bounded by this curve C. So by Stoke's theorem, what we obtain is that this value, this gives us, it is double integral over S, it is f vector, curl of f vector dot ds vector, where S is this surface. So ds vector, that will be normal to this surface n cap. So to calculate this normal, we require the equation of this plane, and the equation of this plane, it is given by x by 2 plus y by 3 plus z by 6 is equal to 1. So this gives us 3x plus 2y plus z is equal to 6. So the value of the normal that we have, it is 3 cap plus 2 cap plus k cap divided by square root of 9 plus 4 plus 1, and this value is equal to square root of 14. Now if we calculate the value of curl of f vector, if we calculate the value of curl of f vector, it is I, j, k. It is curly by curly x, curly by curly y, curly by curly z, and the values we have over here, it is x plus y, 2x minus z, and y plus z. Now if we calculate this curl, the answer we obtain it is 2I cap plus k cap. So if we substitute these values, we have the value of curl of f vector and we have the value of n cap. This ds vector we can write it is n cap dot ds. So the integral becomes, it is double integral, it is curl of f vector dot n cap, we are having it is 1 by root 14 into, it is 6 plus 1 into ds, where ds is, we are talking about s is this surface. So we are getting it is 7 by square root 14 into double integral of ds, that is, this is the area of triangle ABC. So on solving this, we obtain this value is equal to, it is 7 by root 14 into root 14 by root 14 into area of this triangle. Now area of this triangle, it is given by the sides of this triangle, they are, we are writing AB vector, it is 3j cap minus 2I cap. AC vector, it is OC vector minus OA vector, so it is 6I cap minus 6k cap minus 2I cap. So the area of this triangle, it is given by half mod of AB vector dot AC vector, and on calculating this value, the answer you will get it is 3 square root of 14. So we substitute this value over here, it is 3 square root of 14. So the answer, the final answer we obtain, and this value, this will become 14, this is 1 by 2. So we get it is 3 into 14 by 2. So this is equal to 21. So we are saying the value of this integral is equal to 21. Next is apply Stoke's theorem to evaluate the integral. It is y dx plus z dy plus x dz. We have this integration over C, where C is the curve of intersection of x square plus y square plus z square is equal to a square and x plus z is equal to a. So this is shown in this figure over here. We have the sphere, this is x square plus y square plus z square is equal to a square, it is this sphere, and x plus z is equal to a, we are talking about this plane over here. So when both these intersect, we obtain a circle. So if we apply the Stoke's theorems to this, we obtain this is equivalent to calculating double integral over surface S. This is the surface S we are saying, and it is curl of f vector dot ds vector. Now curl of f vector, when we calculate, it is I j k cap, it is curly by curly x, curly by curly y, curly by curly z, and the values we have, it is y, z and x. So the answer we obtain it is minus I cap minus j cap minus k cap. And now we have to calculate the normal to this curve. The normal to this curve basically we are calculating. So n cap, it is given by I cap plus k cap divided by root 2. So this integral becomes, it is double integral, dot product of both these will give us 1 by root 2 is there. Then we have minus 1 into ds. So we are saying this is equal to, the minus sign will come out, it will be minus root 2 double integral of ds, where s is this, the surface of this circle, circle that we will obtain by substituting x plus z is equal to a in this equation. So we have to calculate the radius of this circle. So we are saying, we are having, this is the sphere that we have a plane over here. We are talking about, this is the center of this circle, this is the radius of this circle, and this is the perpendicular that we have drawn. Now the value of radius of this sphere, it is given to be a units, and the distance between this point O and this plane, it is given by the formula. The equation of this plane, it is x plus z is equal to a, and this point it is 0, 0, 0. So the distance between these two, it is a by root 2. So by using the Pythagoras theorem, we obtain that this length, it is a square minus a square by 2. So answer we obtain, this is under root of this, so answer we obtain a by root 2. So the area of the circle that is obtained over here, the area of this circle, it is pi r square. So answer we get, it is 1 by 2 pi a square. So we are saying the integral over c f dot dr vector, that is equal to double integral over s, we have obtained it is minus root 2 into ds. ds is the area of this circle, that is equal to 1 by 2 pi a square. So the answer we obtained it is minus pi a square by square root 2. So this is the value of this integral. Next we have is, if S is any closed surface, we have to prove that double integral over S curl of f vector dot ds vector, it is equal to 0. So we are saying, suppose we have some closed surface, S, and we cut this closed surface by a plane, and we have now two parts, one is this upper part and second is this lower part. We are calling this upper part as S1 and this lower part as S2, and this curve that is common over here for both these surfaces, we have this curve common over here. We are saying this is the curve C bounding both the portions. Then we are saying, when we are talking about this surface S1, I am talking about, this is the surface that we have and this is the curve C we are saying. Now it has to bound this surface. We have another surface over here and this is the curve C we are saying. So if we talk about the direction of this curve C, then the direction of this curve C1, it is in this direction. The direction of this C2, it is in this direction. So we are saying that if we have to calculate the value of double integral over S curl of f vector dot ds vector, so that will be equal to double integral over S1 curl of f vector dot ds vector plus double integral over S2 curl of f vector dot ds vector, and these values, these are equal to integration over C1 f vector dot dr vector minus integration over plus integration over C2, it is f vector dot dr vector, and what we have is that the curve C1 that is equal to minus of curve C2, that is their directions, they are opposite. Suppose we are saying this is equal to C, so we are saying this is over the curve C, this is with minus sign and this is over the curve C. Both these values get cancelled and the answer we obtain, it is equal to 0. So we are saying that the value of this integral, double integral curl of f vector dot ds vector, it is equal to 0. Now next question we have is to verify the Stoke's theorem. This is f vector given. S is the upper half of the surface of the sphere x square plus y square plus z square is equal to 1 and C is its boundary. So we are talking about, this is the upper half of the sphere and this is the boundary C that we have, this is the surface S we are talking about. So we have to verify that the integration of f vector dot dr vector over this curve C, that is equal to the curl of double integral over f curl of f vector dot ds vector. So first we evaluate this value. So if we talk about this curve C, this is, we are saying the sphere that we have, this is passing over here. So this lies in the xy plane and the equation of this curve, it is x square plus y square is equal to 1. So if we change it to the parametric form, we get it is x is equal to cos theta, y is equal to sin theta, we have z is equal to 0 and the value of theta, it is varying from 0 to 2 pi. So corresponding to this, we have the value of dx is equal to minus sin theta d theta, Value of cos theta, it is dy is equal to cos theta d theta, and dz it is 0. So the value of this integral will become, it is integration, the value of theta it is varying from 0 to 2 pi. We have the value of z is 0, so y square z, this term will become 0. We are left with only first term, and we are having it is 2 times x is cos theta minus sin theta, and the value of dx that we have, it is minus sin theta d theta. On solving this, we obtain this is equal to 0 to 2 pi minus 2 sin theta cos theta plus sin square theta into d theta, and if we integrate this value, the answer we obtain, this is equal to, when we solve this value, this is sin 2 theta, and integrating this value we obtain the final answer as pi. So we are saying the value of this integral we obtain, it is equal to pi. Now next thing we have to evaluate is, it is double integral over S curl of f vector dot ds vector. Now if we calculate the value of curl of f vector, we obtain this determinant, and its answer we obtain, it is k cap. Now if we substitute this value in this for this integral, we get it is double integral over S curl of f vector dot ds vector. So curl of f vector we have obtained, it is k cap dot n cap into ds. Now we are talking about the value of curl of f vector dot n cap, that is equal to n cap dot k cap. So what we obtain, we are having ds is equal to n cap dot k cap into dx dy. This is the projection in the xy plane. So this integral we are talking over here, it is double integral curl of f vector dot n cap into ds over the surface S. This is equal to double integral over S. The value we obtain, this whole value we are getting, it is dx into dy, that is equal to, this value we are saying, this is the area of circle in the xy plane, that is x square plus y square is equal to 1 and z is equal to 0, and the value of this area we have, that is equal to pi. So we are saying that in both the cases we have obtained the same answer pi, hence the Stokes theorem is verified. Next is verify Stokes theorems for this function over the cube whose vertices are, these are the vertices of a cube, if the face of the cube in xy plane is missing. Why we are saying so? Because we require the surface to be an open surface, it should not be closed. So we are saying that this portion of the plane, it is missing. So we are saying we have S1, that is the square face MPLC. We are talking about different faces over here. It is MPLC, it means we are talking about this top portion. This is the portion S1 we are saying. Then we have S2, it is the face in the ZX plane. We are talking about this plane, this is surface S2. Then we are talking about S3, it is face PNBL. We are saying this is PNBL, this surface we are saying this is the surface S3. Then we are left with two surfaces, one is this front surface we have, this front surface we have, it is S4, and this surface on the back we are saying it is S5. Now when we evaluate the value of curl of f vector, the answer we obtain, it is I, J, K. This determinant, it is shown over here, and we are having the final answer as minus y I cap minus x times k cap. Now we have to verify the Stokes theorem. So we are evaluating the value of double integral curl of f vector dot n cap into ds. How many surfaces we have? We have the surface S1, S2, S3, S4, S5. We are saying for the surface S1, the value of n cap that we have, it is equal to k cap. For S2 the value of n cap it is minus j cap. For S3 n cap is j cap. For S4 the value of n cap is I cap, and for S5 the value of n cap is minus of I cap. Now when we substitute these values in this formula, we obtain the value of the curl of f vector dot n cap, that is equal to, when you substitute this value you will get, it is double integral over the surface S1. So the answer you will obtain in this first case, you will get, it is double integral 0 to a it is minus x dx dy, and the value you will get, it is minus 1 by 2a cube. For the second case, for the second surface we have the value 0. For the third surface we have the value 0. For the fourth surface, when we calculate this value, we are getting curl of f vector dot n cap is equal to minus y, and for fifth surface we have it is y. So when we calculate the value of the sum of integrals on these two surfaces, when we calculate the sum of integrals, the answer we obtain it is equal to 0. Answer we obtain it is 0 over here. So we are saying these are the values that we have. The sum of all these values, it will give us the value of the integral, double integral curl of f vector dot n cap into ds. So sum of all these values, it is minus 1 by 2a cube. Now next thing we have to calculate is the value of the integral f vector dot dr vector, where c is the curve bounding it. Now when we are talking about the curve C, we are saying we have the figure we are having, it is in this form, and we are saying the curve bounding this, it is in this form. This is O, then A, then N, then B. This is the curve we are talking about, which is bounding this whole surface. It is open from this side, the surface is open from this side. So we are saying along OA, when we are talking about this line OA, we have the value of y is equal to z is equal to 0. Along AN we have x is equal to a and z is equal to 0. Along NB we have y is equal to a, z is equal to 0, and along OB we have x is equal to z is equal to 0. And if we substitute these values in this formula one by one, we are saying along OA f vector dot dr vector, we obtain it is 0. Then this is along OA, because value of y and z both are 0, so dy dz, these are also 0. Similarly, when we are talking about AN, the value we are getting for this integral, it is 0. Then we are talking about NB, we are talking about this line, we are saying it is integration a to 0, we are left with this ax dx, the answer we obtain minus 1 by 2a cube. And when we are talking about B to O, we are talking about this value, the answer, the value of this integral we obtain, it is also 0, because y is equal to z is equal to 0. So this will give us dx is equal to dz is equal to 0, and the final answer we obtain, it is 0. Now adding all these values, we are having these 4 values, adding all these values, we obtain that the value of this integral is equal to minus 1 by 2a cube, and this is what we have to prove. We are saying the value of both these integrals, it is minus 1 by 2a cube. Next is evaluate the integral, it is integration f vector dot dr vector over the curve C, where f vector it is given over here, and C is the curve of intersection of the plane 6x plus 3y plus 4z is equal to 12 with the coordinate planes. So if we plot this curve, we are talking about, this is the plane over here, and it is intersecting with x axis, y axis and z axis at these 3 points A, B and C. Now to evaluate this integral, we are using the Stoke's theorem. So it means we have to calculate double integration curl of f vector dot n cap into ds over the surface S, where S is the surface of this plane. Now if we calculate the value of curl of f vector, we are talking about this determinant, curl of f vector we are calculating, we are talking about this determinant. The answer we have obtained, the calculations you can see, it is 2i cap plus 2j cap plus k cap. Next we have to calculate the value of n cap. So to calculate the value of n cap, we are saying the equation we have it is this. So the value of n cap we have it is 6i cap plus 3j cap plus 4k cap divided by square root of 36 plus 9 plus 16. So this is equal to 1 by root 61 6i cap plus 3j cap plus 4k cap. Now if we calculate the value of curl of f vector dot n cap, we get it is 1 by root 61 into, we multiply these values, we get it is 12 plus 6 plus 4. So answer we are getting it is 22 by root 61. So we are saying the value of this integral will be, it is double integral over s 22 by root 61 into ds, that is equal to 22 by root 61 into area of triangle ABC. Now to calculate the area of this triangle, we have to find the sides. So we are saying this side, the equation of this side AB in vector form, it is minus 2i cap plus 4j cap, and equation of this AC that we have, it is minus 2i cap plus 3k cap. So the area of this triangle, it is AB vector dot AC vector mod, and it is half over here. So the value we obtain, look at this calculation over here, we get it is 6i cap plus 3j cap plus 4k cap mod. On solving this, the value we obtain, it is equal to root 61. So what we have is that double integral over s curl of f vector dot n cap into ds, that is equal to integration over c f vector dot dr vector. We are saying this is equal to 22 over root 61 into root 61, and the answer we obtain, that is equal to 22. So this is the value of this integral. So we have used Stoke's theorem to evaluate this integral. Now next we have is evaluate the integral, it is the line integral f vector dot dr vector by Stoke's theorem. This is the value of f vector, and C is the boundary of the triangle with the vertices 0 0 0 1 0 0 1 1 0. So these are the triangle basically in the xy plane. So if we plot all these points, we obtain the answer in this form. Now for this curve vector f vector, if we calculate the value of curl of f vector, the answer we get, it is, look at these values, it is minus 2y into x plus z times I cap plus y square j cap plus 2x minus 2y times k cap. If we calculate the value of n cap, this is in the xy plane, so n cap will be k cap. If we calculate the value of curl of f vector dot n cap, the answer we get, it is 2x minus 2y. So we have to evaluate the value of 2x minus 2y, it is dy dx, it is in the xy plane, so n dot k will be 1. So the limits now we will have, the limits for y, they are varying from 0 to x, and we have drawn this number, it is 0 to x, and x is varying from 0 to 1. So if we solve this integral, we are getting it is integration 0 to 1 with respect to y, it is 2xy minus y square, limits are 0 to x dx. So this is equal to integration 0 to 1 x square dx, so that is equal to 1 by 3, and this is equal to the value of the closed integral f vector dot dr vector. So this is the required integral. Next we have is find the value of double integral del cross f vector. It means we are saying it is curl of f vector dot ds vector taken over the portion of the surface x square plus y square minus ax plus ay is equal to 0 and the bounding curve in the plane z is equal to 0, and this is the value of f vector given to us. So to evaluate this integral, we are using the Stoke's theorem, and we are writing this integral is equal to integration over c f vector dot dr vector, where this c it is given by, in this equation if we substitute z is equal to 0, the equation of the bounding curve we will get, it is x square plus y square minus 2ax is equal to 0, z is equal to 0. So this equation we can write it is x minus a square plus y square is equal to a square and z is equal to 0. So in the parametric form this circle can be written as x is equal to a plus a cos theta, y is equal to a sin theta, z is equal to 0 and theta will vary from 0 to 2 pi. So we are saying the value of the integral over c f vector dot dr vector, that is equal to integration 0 to 2 pi. We substitute these values in this equation, we will obtain it is a square sin square theta minus a plus a cos theta whole square into minus a sin theta d theta. Next it is plus a cos theta whole square minus a square sin square theta, and it is multiplied with a cos theta d theta. Now we have to evaluate this integral. The calculations, these are shown over here. We are talking about this value, this double integral, it is equivalent to the line integral in this form. Now we are using this result that sine cube 2 pi minus theta is equal to this. So this whole integral it reduces to this form, and when you solve this value, these calculations you can see over here or you can try at your own to evaluate how to evaluate this integral. The answer you will obtain on solving this value, it is 2 pi a cube. So we are saying that by Stoke's theorem both these values these are equal, and the value of curl of f vector dot ds vector, that is equal to 2 pi a cube.